Hello, everyone. Welcome. This talk is going to be about origami software, software that came before me, software that I wrote, and a little bit of my own personal journey folding paper. Okay, so I've been folding since I was 6 years old. At this point, I'll fold anything. I'll fold in any style. I've folded pieces that have only been attempted a couple times. However, I am a complete beginner at origami design, and I am suddenly I need to change this about myself. I need to be a contributor to the origami community. I need to figure out how to design origami. And so a year ago, I set out to do this. I resolved to figure this out. Oh yeah, I'm going to use this. Okay, so I think about this quote whenever I approach something new. I got this from Philip Glass. It's in his documentary. So this pertains to music specifically, but you can probably find it being said about other art forms by other people. So in the case of origami, my experiences, I encountered curved creases were probably the thing I was most fascinated by. They're maybe the most unsolved problem. So I started there. I'm going to explore some curved creases on my own with some of my creative coding experience. And I got some cool, interesting things. But one thing you'll notice is a lot of these designs, they don't collapse in on themselves. There's not too much material hidden. And I also kept hitting walls. And I knew that these walls were because I was avoiding what I knew I needed to be doing. I needed to be learning classical origami design. How do I fold an animal, a flat foldable animal? That was my challenge to myself. I was going to figure that out. Okay, so I set out to do this a year ago, and it's been a slog. I spent like 4 months trying to fold a dog, and I failed. 4 months amounted to nothing. However, this spring, I got something. I made a crane of my own design, and I'm so proud of this. I can't tell you. Thank you. Okay. However, this crane design becomes three-dimensional very early on in the folding, and it's a little awkward to teach. I thought this was close, but it's not quite there. Something caught my attention about sea turtles. I thought that maybe there was an opportunity there. And then just a couple months ago, I did it. I got a sea turtle design that folds flat. So while I was doing this, I'm going to switch over and talk about software in a second. But as I set out on this quest, I also started to build my own software. So this is my software rendering my crease pattern and the flat folded state on the right. And I thought, okay, so people build sea turtles. By the way, here's one of the prototypes of it. So people put shells on sea turtles. This is a thing. Origami artists have been using hexagons. Can I take it a step further? Let's map a real turtle shell onto it. I threw it into my software, and it gave me back a turtle shell mapping. And I've got a turtle shell on a turtle now. All right. So let's dive into software. The software that came before me. I'm not going to talk about TreeMaker very much, but I'm going to go over the other three real quickly. So I need to say, why am I writing software? Good question. If you look at Lang's work, around that time, when he made TreeMaker, suddenly he was able to take a deer and take the mapping of the deer's antlers and the branching pattern and then the ratio of the branches getting shorter and replicate that directly in his work. And he was able to do that with the software that he wrote. People are able to. So I have to write my own software. What's my thing that I'm going to build, right? Okay, so let's talk about Reference Finder. I used Reference Finder is probably the software that's used the most in origami. And let me show you a use case. So here's my turtle base that you all just saw. When you open it up, there's these sets of lines up here at the top. They relate to each other. And then there's these set of lines down here, and they relate to each other. The trick is I need to find, when I'm folding this, I need to find either of these. The trick is that these depend on this position, and this position depends on this position. So you end up with this often in origami, and hence this software. What I did is I designed this piece, I figured out what this point is, and then I throw it into Reference Finder, and Reference Finder will tell me how to find this point using the origami axioms. Put a note on that. We'll come back to axioms in a second. And with just a few simple folds, it'll find the thing. And notice that there's errors going on. You want to pay attention to that when you're using the software. Okay. So software number 2. Let's see, clicker, you got this. Okay, software number 2, Aripa. Think of Aripa as Illustrator, helps you draw out crease patterns, all right? The thing that you get for with Aripa, though, however, is, and if you fast forward, it will simulate the flat-folded state. So it will fold your crease pattern for you. Okay. So 2005, I think that's right. 2005 was when this came out, and I say this because there was a minor little revolution that happened in that moment, because suddenly we could design with algorithms in a new way. And I want to talk about this one artist, Ray Shamp. This is one of Ray's pieces. I love this piece so much. This piece was made with a few simple maneuvers in Aripa. You draw these diagonals, and then you draw one of these units, and then you use Aripa's reflection tool, and it goes across the entire piece. This piece is flat foldable, and I love it. What I have up here is one of Ray's pieces as well. And do y'all know Black MIDI? Yeah, where it's just. Oh yeah, you have a question.
What's flat-foldable mean?
Oh, good question. I know I'm going to answer it later, but I'll just answer it right now. Flat foldable means, so this, let me show you something that's not flat foldable. This is not flat foldable because it has parts of the paper sticking out of a plane. Yeah, okay, and when I had this thing all collapsed up, which I could do it real quickly, the base of it one little catch right there, and then okay, this lies in a plane. Yeah, flat foldable. Okay.
When you hold up your examples, can you hold them up in the light of the projector, because that's easier?
Oh yeah, totally.
Thank you.
How's that?
Yeah, that's better.
Thank you for this feedback. I appreciate it. All right. Okay.
You're on
So-
Black MIDI.
Yeah, Black MIDI. Black MIDI is where, just Google it if you don't know. It's like streams of notes. It's like you make it by using MIDI software. It's kind of a hilarious take on like music making, but I thought that this might be considered like Black MIDI of crease patterns. Nobody's folded this. I don't think anybody would ever want to. Ray certainly hasn't, but. I think that it's flat foldable. I still need to ask him about that. At least these units are. Okay. Might have to switch over to the mouse. Okay, last bit of software. What was that, 2008? Origamizer, Tomohiro Tachi. Tomohiro Tachi's software helps me fold this. This is the Stanford Bunny. Also not flat foldable. It's not meant to be. what I did was I simplified the Stanford Bunny model in Blender, fed it into Tomohiro's software, and his software gave me this back. And then I folded this. And now I colored it based on my experiences writing my own code. I was able to parse what is even going on here because this is such a new paradigm of origami design. And I really wouldn't have been able to fold it or just really get an idea of what's going on if it hadn't been for my experiences building origami Voronoi out of my software, which I'll get to in a bit. Okay, so Robert Lang told me the words planar graph, and I went on my journey. A crease pattern is a planar graph. It's like the first screen of Zelda. So here's been a couple, a little like snapshot of my last year building this software. A planar graph, what is a planar graph? A planar graph is built on a graph, mathematical graph, nodes and edges. Graph, I built the graph. I switched over to TypeScript at the time. TypeScript is great, by the way. I'm a big fan of that over JavaScript. So graphs, planar graphs are built on graphs. My graph works beautifully when all the adjacent nodes and adjacent edges, like these are discrete answers. They give me back the right answers. You clean a graph, everything works perfectly. When you move to planar graph, however, it gets so hard. Because of the epsilons. It's all because of the epsilons. When you have lines that are almost parallel, do they have an intersection? When do you consider them parallel? What I found is I ended up having to write all of the fundamental 2D geometry stuff myself, and ended up just rewriting it. There were times when collinear intersection, when a line intersects a line from below, it registers the intersection, like when it's like on the line. Collinear is what that means, when it's just right there. But when it was from above, it wasn't registering it. What's going on? Okay. So I have a couple screen grabs from inside of the code. What I was just referring to, this is from only inside of the planar graph data structure. Some classes and then some of the functions, some of the geometry functions. Things that I didn't actually think I would encounter. I was going to mention the clockwise angle from function. Okay, so have y'all encountered the thing where one node, two rays extending from the node, all right? And when you're doing the whole like atan2 math cosine, etc., you have this 0 is that way to positive 180, 0 to negative 180, and you have to measuring an angle across that negative 180, positive 180 thing. That's a thing. There's a whole thing around that. Stack Overflow has answered this thing for us. Thank you. But what I didn't anticipate was, okay, so just measuring the angle is fine, but what if I need to know the clockwise angle from one to another? So here's two rays coming out. There's two angles. There's this angle, and then there's this angle. And how do I figure out which one is clockwise? It's actually a real simple and elegant solution, but I had to figure it out. Stack Overflow didn't know that one. So this has sort of been my last year building this thing. Okay, so I think now I'm just going to start demoing some software. Escape out of here, over here. Okay, as I was working on this, I was building visual tests and throwing them up on my local host so I could just keep track of what's going on. So as I'm building this, I start to build things around it and realize that I'm building the documentation. Documentation is the tests, and I can go back, and very useful, it would break things, and I could go back here and just check what happened, if everything still works. So here's a page just describing the epsilon that I was talking about. When do you consider two things in the same place? This fragment function, just hovering the mouse over it, it's clear like what this function is doing. It's chopping the edges up right there. And then that's important because I need to find the faces in a crease pattern. So I am walking down, I use the edge walking where you walk down most immediate right turn, keep doing that until you end up where you began and you found a face. But the fragment function needs to be just like error proof. Another thing, real quick, is like when you're removing nodes, so these are two edges right here. When I remove this edge, it identified that one node to be a co-linear node, and it will remove it and merge those two edges into one. I feel like this is a game, by the way. Minimum number of clicks to remove all the edges. If anybody wants to make that, please. Okay. Okay, so I mentioned axioms. Let's talk about the axioms for a second. These are the, for putting a crease onto a page, there are 7 ways to do this. Given 2 points, you can fold a line between them as such. Given 2 points, same inputs, you can fold a line where you put the 2 points together. And then this one was cool. This one justified my whole reason for doing this to begin with. I had been introduced to axiom 3, something like this, where you get one line back, right? Crease a line to a line, and you get a line that's kind of running through the middle of them. It didn't occur to me that there were 2 lines possible. Like maybe I would see this example, and I would still see the blue. I would just see the blue line whenever I would be given that command. It didn't occur to me that there's 2 answers, 2 results from axiom 3. Axiom 4, and then this is about it. As far as practical origami as a folder, we really only use axioms 1 through 4 in our actual practice. Because they get kind of cool and kind of weird. But here's another one that gives you 2 results back. Axiom 6. Open invitation. I'll put your name up on here. A lot of these use compass ruler geometry. And it's been a joy to build. It's the math that I really enjoy. That one happens to be extra complicated. Axiom 7. Okay, so these are the 7 origami axioms. Okay, so this is what I was thinking about when you asked that question. I am going to go deep into depth about what flat foldable means. I'm checking the time to make sure. I'm going to explain to you all how this algorithm works. You're going to leave today knowing this. How do you turn a crease pattern, on the left, into how do you simulate the flat-folded state on the right using a computer? Okay, things to notice. The crease pattern on the left doesn't have any mountain-valley lines. We don't need that for this one. And then the folded state on the right is translucent. Those are key things to think about.
Is a mountain-valley line the dotted line?
Oh, so they are represented by different, there's actually competing standards, but a mountain and valley line is, if you look at this on edge, this is a valley line because it's making a valley, and this is a mountain line, it's because it's making a mountain. And if you flip it over, a valley becomes a mountain and a mountain becomes a valley. It doesn't exactly matter which one is which, but that they are opposite. They're opposing each other. Yeah, okay. Okay, so let's dive in for the simplest case. Fold one crease. We're going to need 3 tools to accomplish this. So tool number 1, we're going to need a reflection matrix. Okay, so here's how we do this. We pick one face. It's going to be the face that's always going to stay on the table, and then the other faces are going to be reflected. So a reflection matrix, we need a reflection matrix a little special because we need this to not just reflect through the origin, which is what this reflection matrix is doing. As you see, just the four numbers are moving around. We need a translation column so that we can move away from the origin, and that last column will move too. So what we do is we build a matrix that reflects a polygon across one of its edges. That's all we need. Bring that back to here, and we reflect the top polygon across its edge. That's really simple, right? Like I feel like everybody's probably following along. Okay. Good, good. Step 2, take what you just learned, do it with this, all right? Same thing, pick a face. It's going to be the face that stays on the table and doesn't move. Let's make that the far left face. Do the same thing we just did. Step to the right. So let's store that reflection matrix on that face, all right? Let's do it again. Step to the right, and let's store that local reflection matrix on that face. So we're just the line that we just crossed from the parent to the child all the way down to the leaf node. All right, each face is storing its local reflection matrix. And then when you apply the algorithm, the leaf node, or in this case, any face will get multiplied its reflection matrix times all of its parents' reflection matrix up till the root node. Okay, a lot of nodding heads. Okay, y'all are great. Y'all are following me. Okay, so what we just built there was tool number 2, what I'm calling like a adjacent face tree, where we are just from root to leaf, the path of who's the parent and who's the child, because we need to know this because you need to be able to apply your parents' reflection matrices. Okay, essentially we've made it. Here's this. Here's that data structure that we just built together, visualized. I'm using the mouse to just change whatever the root face is. Okay, so what we just did will accomplish the flat-folded state. However, there's one thing that I know that some people are thinking about right now, and I'm gonna talk about it by focus on these two triangles right here. Do y'all see those? The small ones? I have to move the mouse back, but those two small triangles are leaf nodes from different branches, right? However, they're touching each other. Okay, so you're imagining this algorithm, applying this algorithm, these faces. So essentially, you're cutting the paper between all the pink lines, right? You're cutting the paper where those two faces are. These faces fold up, and they go on their journeys up, down towards the root node. How do we know that those two faces are going to line back up again in the end so that edge, they're sharing that same edge, you know? How do we know that? The trick is tool number 3. And if we can prove on every node on this crease pattern that every node passes Kawasaki's theorem, which is very simple. Those are four lines sharing a vertex. Count up, and this works for any even number, 4, 6, 8. Count up all the evens and all the odds, every other one. Each sum of each angles equals 180 and 180. If that's the case, if you can prove that for every node on the crease pattern, then that thing I just said happens. The edges will line up. It's not, because it's not the case for every SVG you throw at it. If you did that, if you applied that to an SVG, faces they would do their thing. They would be all over the place. But if you can prove Kawasaki's theorem, that's the only thing. That's the third thing we need. You can apply Kawasaki's theorem on every node. Then that's it. You do this reflection matrix thing, and you'll get everything showing up right in place on the right. Oh, yeah.
Is proving that theorem
picking where you start the root doesn't matter. Yeah. It's just to say, if you were to apply this algorithm, would the paper be like, end up where it, like next, all the faces next to each other, sharing the edges that they need to share? Yeah.
Is it possible that there are multiple solutions though? Like that it could look very different?
Oh, you know, I thought about this, and I couldn't.
Repeat the question.
Oh, thanks. Yes. So the question was, is it possible that there are multiple solutions? I think that, I don't know the answer to that, but my speculation is that there's not. Everything I was throwing at it, it's showing me one solution. Let's talk more about this. Okay. So some things that I have built with my software. Here is the crease pattern validator. It's doing what you all just learned. Kawasaki's theorem. The projector is making that a little small. I didn't expect that. That should be bigger. Sorry. Let's see one with errors. Okay. When I design, so here it is. It's pointing out which spots are not passing Kawasaki's theorem. So when I built my, when I designed my sea turtle, I'm building like the more complicated base. Here that is. I made some errors. By the way, wouldn't it be great if I could just grab that? Like, I know that it's close. That's the thing. If I could just say, computer, just wiggle it around or something. I know it's really close. So I built that. Here's a crease pattern that that I got from Ray Shamp's GitHub repo. And Ray, I finished your crease pattern for you. Yeah. Here's one where you can see it a little more in action since that one had a lot of nodes. Yeah, so here's the cool thing is you can sort of move it around in real time, and as long as you're gentle with it, you can sort of, you can change the shape of it as it's wiggling into place. Okay, so let's go back to Aripa, the Illustrator type application where you're inputting lines. The thing that I still remember when I first opened it up, it felt like how academic software sometimes feels like, where you look at it and you're like, I don't know what to do. I can tell that this application is asking me to bring my master's degree to the table. And it doesn't need to be, is the thing. We just learned the origami axioms, right? With a blank sheet of paper, there are 4 creases we could make with these 7 axioms. Actually, right now I have it running only 3. So let's show the people those possible creases we could make. Here they are. And if I want to pick one, I select it, and it shows me all the new creases that open up. So you're not asking anybody to bring required reading to this application. They can just sort of click around and sort of explore it on their own, right? Problem is, you'll notice that this, as I add one more line and then maybe one more, it gets really complicated really fast. I think that there's something quite beautiful about this shape, and but as far as a practical tool, if I want to crease this bisector right here, that's hard. That's too hard to do. So what we need is a different method. I'm exploring this right now. Maybe we can do something like this, but also something a little predictive like this, but also give the user a little more control over what they're trying to aim for. Okay, so same type of tool I've built here. You all, we talked about Aripa. Let's talk about Reference Finder again. When I'm designing this turtle, let's revisit that point again. So I've designed this turtle, and to fold it, I need to find this point as a reference. Reference Finder will do that. The only thing that I wish that it would do is, for my design, I know that I'm folding it into thirds. I know that I'm folding like from that, I'm folding these 45s up, and then, so what I know is I know that I'm putting lines into it. I have a certain set of lines that are definitely going to be in the piece, and I would wish that Reference Finder would consider those as a part of their equation, or to sort of prioritize those in its equation. So what I want to do is I want to find my point, which is 288, so about right there, and it turns out there's a line. Did it zoom? Yeah. Y'all can see that. There's the line. Using the lines that I know are going to be in the piece already, there's an axiom 3, which is my favorite axiom, by the way, line that takes me right to where I need. And this is how I fold the piece now. I use this. All right. Okay, so last thing I'll share is that I've finally gotten this library to like a working state, and I can begin to have fun with it. Actually, I'll put up some diagrams here. Here's a Voronoi diagram generator, and it happens in real time, so you can really explore it like that. So I use that to build this, and it's just as easy as hitting the download button and then sending it to your creasing machine. Yeah. Yeah. Okay. So what do I want to say about this? I had a thought, and it's escaped me now. Must not have been important. Okay. What was it? Okay. Okay, back to the presentation. Okay, so, oh, right. So I just remembered. This slide helped me remember. I'm building it in JavaScript. I'm building this library in JavaScript. It's intentional. I wanted this to be on the web. I wanted there aren't many origami artists out there. We are all spending time alone in our bedroom. I wanted to fix that a little bit. So with regards to that last example, I was using D3's Voronoi algorithm, and that was the other reason I picked JavaScript. So the community, and then let's be able to tap into all these tools that are available to us, right? Okay. Something I'm really keen on doing is making it like as close to a one line of code as possible. So this will throw up a crease pattern up on your DOM. If you include the source files, there's always more than just the one line. I spend a lot of time with creative coding applications like processing and open frameworks. And what I did was I built a wrapper around paper.js, by the way. Paper.js, how about that? That's what I've been using to visualize it. So I built a wrapper around paper.js and called it origami paper. And so you can make an origami paper. And I'm modeling this as close as possible. You can see to some of these processing type of programs. So this is sort of like your empty project. Like if I handed this to you all, jam on this. You got an idea of like how to interact with it. Okay, so here's some of the ideas I'm exploring. Whenever you make a crease, it stores how it was made. If it was a certain axiom that was made, what were the parent creases that made it. So I could design a piece on a square piece of paper and then perform it on a rectangle. And maybe it will fail at some point, but it can attempt it at least. And maybe it would come up with something that I didn't expect. if we have this system where lines know where they came from, we can auto-generate diagrams. Now, diagrams are the things that if you open up an origami book, it starts with a square and it has an arrow drawing in a dotted line, right? These things can be auto-generated now with this type of data. Just like trying to like push the boundaries, like if we have this data, like can we ask the computers to start to design? If we actually get these large data sets, can we do machine learning on it? So thank you all very much for listening.